Hello and welcome everyone. So we have dwelled on the path of expert data analysis, and in that we were in the middle discussing about different things that are to be done with data, and we started with handling missing values, and then comes you can remove duplicates. But in today's session, what we'll do is we'll see how to explore the data more. So we'll do this EDA. We'll delve more into this EDA, explore data analysis. There are different types of analysis. You can do univariate analysis, you can do bivariate, multivariate analysis. Okay, I'll just write them. Univariate analysis, you can do bivariate, or you can do multivariate. Okay, meaning is pretty clear. So univariate basically means you will use just one variable to analyze things. Okay, just to remind you once more, whenever I make data matrix like this. So okay, in which I have these rows and columns, and each of the row I call it a data point, or it's called a record. So here we have these features. So these things over here are features. This, and these are features. Okay, there are different types of problems: classification, regression. Okay, and based on that we say if they're a target variable or not. So these features, let's suppose if it's a supervised setting, and if it's a classification problem or a regression problem where we're having a target, so in that we say that these features are also called as independent variables. Okay, and the class is called as dependent variable, or the target that we want to achieve, and this we call as a data matrix. You'll hear it quite often from me that we'll call it a data matrix. And once we have this data, now we have to analyze. Okay, we have to set a target. We will be having some goal in our mind. Okay, this is the thing that we want to achieve. Keeping that goal in the mind, and then we'll analyze the data. We'll act like, as I was saying, that there is a meme floating around that you'll point a gun at this data and ask it a lot of questions. The questions should surround that, because you want to get information out of it, and that information should somehow steer you towards your goal, that the goal that you have. So the dataset that we are discussing, dataset we had is iris dataset, iris flower dataset. This is what we started with when we started doing exploratory data analysis. Okay, in that we had 4 features. We had sepal length, sepal width, petal length, and petal width, and then we had a target, that is class or species. Okay, and it is a classification problem. We have iris versicolor, we had virginica, and we had setosa. These were the classes, and these all things were the numerical things that we discussed in the session 1 when we are doing this EDA. Now if you do this, if you perform unit analysis, you should only use one variable to perform the analysis, and then in bivariate you'll probably use 2 variables, and in multivariate you'll use multiple variables to do the analysis. Okay, now I'll make the goal clear. This is what you should have always in mind. Okay, that's when I said whenever you're doing something, you define a problem statement. So when you define a problem statement, you define it because everything that you do is basically somehow taking you to that solution. Okay, it should somehow take you to the solution, and maybe in the middle of doing the analysis, you might change the problem statement itself. You might think that, okay, this problem, the problem that I formulated is not achievable, or maybe we can reformulate the thing and we can do something else, and it will get clearer once you go on to that path. So first we should be clear with the goal. So this is a really simple task that we are doing. So what we are doing is, given these features, by features I mean petal length, petal width, sepal length, and sepal width. These are the features. Given these features, we should come with a class or the species. Okay, this is our problem statement, or the goal that we want to do, that we want to achieve. So we have to perform a lot of things. So why are we doing this EDA? Because sometimes it's not good to just go with the complex model. You are thinking, okay, transformers are the most complex and comprehensive models that are there, so okay, let me just feed this data into transformer. So it is like maybe if you have to kill, let's suppose, an ant, you are using a machine gun or something. Okay, so it is better, like when you analyze the data, you see, okay, this is the model that suits us better, and this is the model which has very less complexity and it gets the job done. So if simpler model gets the job done, so there will be a lot of advantage that it gives. Okay, so that's why we are doing that. That should be also the goal. So in order to decrease the complexity in terms of resources, in terms of time, and other things as well. Okay, so right now we have the goal in our hand. So we have these features, and based on these features we have to define a class. So that's what I said. You can do the initial thing that you can do is univariate analysis. By univariate, I mean it should focus on exploring the individual variables in the data set. Okay, for this iris data set, we can take this sepal length, sepal width, petal length, and petal width, and we can do some sort of analysis on that. Okay, in that we'll have descriptive statistics like mean, median, mode. I think we have seen this mean, median, mode. Is there something else? So like let's suppose minimum value, maximum value, then variance. We can have standard deviation. So all of these things. So these things are called as descriptive statistics. Descriptive statistics. This will give you people a rough idea about what the data is, what's the mean. I think we have seen that function dot describe. You have the data set dot describe function of that. Okay, and then once you have this mean, median, and mode, this will give you central tendency, and this min max will tell you, okay, what's the mean value and what's the max value. Then this variance and standard deviation will give you the idea how much spread is in the data, and a lot of things can be added here. Okay, it depends on the data set that you have. So that's the first thing, that you have to understand the data set. And after that, now we can do some other things on the data. We can plot some plots. Okay, and based on those plots we can take decisions. Let me just start with maybe some plots. Let me start with this histograms, because histograms, as you know, we have seen that in pandas, and we'll use matplotlib pandas seaborn in here, so that we'll plot these plots over here. So in histograms, what we'll plot is, we'll plot all these features. Let's suppose we'll see how does the sepal length look like, how does the petal length look like, okay, in the histogram, what sort of distribution does it follow. Okay, once we have that, and then we may take some observations from that. Very important thing that I'll mention here is, whenever you do anything, let's suppose right now I'll be plotting histograms. I'll be plotting histograms, let's say. Okay, once I plot these histograms, based on these I should write my observations. This is very important. Okay, many people sometimes miss it because they think that we'll remember it somehow, and then what they end up doing is they don't remember it, because you have to keep on doing this, because this work will probably span through months or years sometimes. So you have to write these observations. If you did something, it's not just for the plotting. So right now I'm showing you the plotting. You should follow this standard procedure everywhere. So you're doing something, you're doing exploratory analysis, you are understanding data, so you should write these observations. You should write the observation. This is what I observed, and that can be your hypothesis in the future, because you can make an hypothesis. We can make an hypothesis based on what you have observed. You can say, okay, I observed this, so this is my hypothesis. Then you can do hypothesis testing and stuff like that. But this is very important. I've seen a lot of people missing it. So they do observe things from data, but they don't write these observations. So you should document these observations. Document it. This is very important when you are doing it. So that's what we'll do here. So the first thing that we'll see is, we'll see these distributions of different features based on the histogram, because histograms they represent these they represent a single variable, and they represent frequency. So this will come under the univariate analysis. Okay, let me do that. And what we can do also is, we can also print the details of the data set that we have already done. So let me just do that as well. So let me bring up the code window. I hope this is visible. I'll import all these necessary libraries. So this is pandas, numpy, matplotlib, seaborn, sklearn, and in the dataset I have this iris dataset. I'll name it. Let's suppose iris, because I have already loaded that, but I'm not sure what I have named it. It is better to load it again. This iris, load iris. So this is my dataset. The first thing that what I'll do is, I'll convert it into a data frame. Okay, let me do this. Okay, if I just print it, iris dot head, I also need to put target and species. So here, let me just paste this one also. So this is species, iris dot target, this is species, and then I'm putting this lambda function to the target names. So let me just put the basic info. So if you see this sepal length in centimeter, sepal width in centimeter, and this is all those things. This is the head of the data set, and now we have these things, because there is this function dot info, and then you can have this describe as well. So howsoever you want to see it. Now I'll plot some histograms. Okay, let me just set this theme for seaborn. So you can see it. We are setting a style for these plots, and the numeric columns are these columns. and then categorical column is this species column. Okay, what we'll do is we'll plot these histograms for all the columns. Okay, so I'm saying for columns in these numerical columns, because these are my columns which are sepal length, sepal width, petal length, and petal width. Okay, and then for columns in this numerical columns, I'm plotting this figure and I'm saying histogram, giving the data and converting them into 10 bins. Okay, then I'm saying sky blue color, and the edge color is this. Alpha is how much transparency you want. I think all of you know this. So if I just run it, this is what I got. Okay, so you can see the data over here. You can see histogram for sepal length, and this is histogram for sepal width, and this is histogram for petal length, and this is histogram for petal width. And you can see the bin, number of bins over is 50. You can change those bins also. Okay, you have to see observations from here. So if you see the observation, let's go to the sepal length. Okay, just give me some time. So then we come to petal width and petal length. So if you see this sepal length over here, so if you see this, so somehow it is normally distributed. Okay, somehow it is like this, but it's a bit skewed. Okay, so if you just draw these points, somehow you can see this is normal distribution till here, and then a bit of skew over here. So that's what you can observe from here. And you can see most of these sepal, they lie between some 5.0 to 6.5 centimeters, because most of these sepals, like from here to, let's say, from 6.5 till here. So you can see this. So most of these sepals lie around here. Okay, so these are the observations. So these observations says that below less than 5.0 and higher 7. There's a very less range. If you see, this is very less over here, and if you see this higher than the 7, there are very small points. Okay, so based on this histogram of sepal length in centimeters, so you can write observations. So I'm giving rough observations. Okay, you should not ask me any questions based on this. This is what I observed, so I'm just giving rough observations. Okay, the first observation is that the distribution of sepal length is approximately normally distributed, and we'll see these distributions in detail, but here I assume that you know a bit of normal distribution, that is symmetric curve, something like this. And then with a tail, with a skewed tail, something with a tail, let's write it like this. And then you can see, okay, why do the most flowers lie? Let's say if we take most of this portion, okay, what you can say is, let's say from this 5.0, so this is the bar for 5.0 and this is the bar for 6.5. so most of these lie between 5.0 to 6.5. okay, this is what you can lie, and very less flowers lie after 7.0. so you can see very less, and maybe even below 5 there are very less flowers. I think you have a question. Yes, go ahead. The question asked was when we are seeing the distribution of a particular feature in the data set, so which distribution is good? If we get that distribution, we should feel okay, we should feel good that okay, we have something. The short answer to that is, if you get a distribution that is somehow good, well studied. Okay, there are distributions which are well studied. Let me just go over here and make this. So what I'm saying is, the question asked, I think I made it clear. Now you're observing some feature, and what is the good distribution that we should be happy about? So as I said, there are some well studied distributions. Well studied distribution. One of them, let's suppose, is Gaussian distribution. If you somehow get the distribution which is well studied, and you will get a lot of material, because other people have recorded a lot of facts about the distribution, and there are a lot of things that are known about the distribution. If you get something like Gaussian, and there are a lot of things that you can know. Okay, because you know it's a symmetric curve. If I know something of this, and I know, let's suppose, many of the data set belongs to this and that, and there are a lot of rules that do follow. There is something called as 10, 30, 60 rule. A lot of things are known about the distribution. Somehow if you get a distribution that is well studied for data, you are in luck, because you know a lot of things about the distribution. And we'll see that why are these distributions even studied, because if you see this Gaussian distribution, somehow it is followed by a lot of things. If you see heights of people follow Gaussian distribution. Okay, and if you know heights of people, where is it used? So it is used, let's suppose you are owning a t-shirt company, you want to make t-shirts. So what you can do is you can ask, okay, you are making a t-shirt for the company which have 80,000 employees, something like this. So if you ask them, give me the sizes of all the people, so it will be very difficult for you to come up with the size. So what you can do is you can just take a sample, maybe let's suppose of some 200 people, or maybe let's have 1,000 people, okay, 1k sample, and you can think, okay, let's see what the distribution. So you will see that it's normally distributed. So when you know that this is normally distributed, so you can make the t-shirts for these 80k employees normally distributed. So because you know a lot of things about the height, so once you will see that you will almost get accurate. Okay, because heights, the people, they are normally distributed. That's why these things are very well studied. We'll see that these things in probability, but just answering your question. So if you have the distribution which is very well studied, and if you see a feature following the distribution, you should be very happy, because you'll get a lot of facts out of this, because that distribution is very well studied, and if it occurs very frequently, you can get a lot of things from the data. Okay, I think that answers the question. Any other questions? Okay, so what I said is there are some models which are called as Gaussian mixture models. So in that, what we do is whatever distribution we have from data, because usually we don't know the distribution and it does not follow a particular distribution. Very rarely is the case where it follows the exactly the same distribution which we have studied about. So Gaussian distributions are very well studied. So what we try to do is we try to fit these Gaussian distribution models or these data that we have. Okay, and then because these Gaussians are very well studied, let's suppose if I have data set like this, just taking a little bit of digression over here. If I have data which looks something of distribution like this, okay, and this is not Gaussian distribution. So what you can do is somehow, if you can come up with 3 Gaussians, you can come up with this Gaussian, and you have a Gaussian like this, and you have a Gaussian like this. If you can somehow combine these 3 Gaussians, that's why it's called mixture of Gaussians. You mix them together, and then you can somehow approximate the distribution that you had actually. Okay, and what distribution actually the data follows is a very hard question. That's what I said. If you know the distribution that data comes from, then machine learning is not needed, even deep learning is not needed, nothing is needed then. So here we assume that we don't know the distribution, and whatever data we collect, so somehow it is the representative of that distribution, and we're trying to come up with the distribution that we see in the data. Okay, so it is a very good question. I got a chance to answer many queries.
Sir.
Yes, go ahead. The question again asked was, okay, why are we somehow cleaning this data, or why are we trying to see what distribution is the data following? So what I said is these models, whatever models we have, either ML models, deep learning models, from the data they try to learn the distribution. We have the data, and because we don't know distribution, okay, this distribution is unknown to us, okay, and they somehow have to learn that distribution. So whatever questions we ask after that, they should be able to answer that question, because they are somehow learning the distribution. So distribution somehow is signifying the pattern, and it has to capture that pattern. So this data, we assume that this represents the distribution, and models have to learn some of the distribution. So as I gave an example, so if you have a Gaussian model like this, if you have a Gaussian distribution like this, if there are 2 parameters, there is a parameter mu and there is a parameter sigma, that's mean and the standard deviation. If you give me these 2 parameters, because Gaussians can be of different types, so one Gaussian can be a peak like this, so one Gaussian can be a little like this, okay, a little fatter. So if you see this spread over here is less, and if you see mean, okay, if you see peak is high, let's say, okay, the value of mean, something like this. So you can have a lot of types of these Gaussians. So all of these variations come from different values of this mu and sigma. So there are 2 parameters that a model has to learn, assuming that the data is following the Gaussian distribution. Okay, now in the real world, data is so complex, and we cannot even quantify that distribution by just making a bare mathematical equation or making a closed form equation. So what we try to assume is we try to somehow give it a distribution in a learnable fashion. Okay, you can give the data as such, you can give it in chunk format, but that representation will be quite hard to learn. So in order to simplify that distribution a little bit less, so what we try to do is, so we try to smoothen the data, we try to let's suppose give the data in such a fashion so that we as the engineers make sure that the model learns that distribution, and it is easier to learn, because at the end of the day this model somehow learns a complex function. So this f of this will be a lot of parameters in that function. So this is what they learn. Okay, now going ahead, you saw the distribution, you saw these histograms. So from the first histogram, what I said is when I show you the code again, so if I show you this code, so you saw that this distribution is somehow following this normal distribution with this skewed tail. Okay, so why am I saying you this? Because you should have a habit, whenever you are doing something, you should have a habit of writing these things down. Okay, you should have a habit of writing the observations, because you won't remember everything. Okay, this is the first histogram that we saw based on the sepal length. If we see the sepal width, you see this is much of the Gaussian distribution. This is more like the Gaussian distribution, and even it does not contain that much of tail. Okay, and then coming to this, if you see, this is somehow bimodal. So if you can see the two modes, so what I mean by bimodal, you can just fit something like this, and there is one more mode like this. Okay, this distribution is somehow bimodal, and you can see there are no points that lie between these 2 to 3 value. These are all the observations that you should write. Okay, if you now see the last plot, if you see this, so this somehow looks very random. It looks skewed, distributed, complete skewed, not even skewed. So this somehow I cannot quantify it again, but still you should write, okay, there are a lot of values which are between, let's suppose, 0 to 0.25 range. Okay, this is the highest value. There are 40 flowers which have the petal width of this much. Okay, and all these observations should be written down. I hope this is clear. Okay, let me go ahead, because we are doing univariate analysis. The first thing we did is, in the previous session we saw that mean, median, mode, and all these descriptive statistics, and then what we can do is you can plot all of these plots to know a lot about these things. And now what we can do is we can also have these interquartile range box. We can plot this Box-Cox plots and a lot of things. So let me just draw that, also these things. So if you see these descriptive statistics, I just had a cell over here, I just wanted to paste it over. So this is for the numerical columns. So you can see numerical column mean value, and then median value, and then I have mode value over here, standard deviation, I have variance, then the range. Okay, range basically is the max minus the min value, and then I have these quartiles, 25th quartile, 50th quartile, 75th quartile. Okay, and then I have this interquartile range, and the last one is I can visualize it. These are all the descriptive statistics which we also saw in the previous session, and you can see them also over here. And then if you can see this Box-Cox plot, it somehow contracts all this information into one plot for all these. If you have sepal length, you have sepal width, you have petal length and petal width. So you can see this Box-Cox plot having this max min value, interquartile range, these median values, and all these things are summarized in this plot. Okay, now what we can see is we can after these histograms. So let me again, we can also have density plots. Okay, how to form these density plots? What you can do is you can just smooth now, because I told you there's an algorithm called as KDE. So kernel density estimation is used, and from that you can just come up with the density plots. They'll be just smoothed out histograms, but we'll take a detailed treatment of one once we go to probability. Then you can also have CDF, PDF, and make these violin plots. We have seen a lot of these plots, and then you can see the count. You can make pie charts. Okay, I have a cell for that. Let me just paste it. That's not difficult to understand. If you see this, so this thing we have done histograms, and then we have these density plots. Okay, this is KDE plot, which is basically smoothed out histogram. So then you have these numerical, you can draw box plots for these numerical columns. You can have these violin plots where you have these CDFs, because we have explained what CDFs are, and then you can also have these bar charts for these categorical columns, and then you can have pie charts of the distribution of these categorical data, how these were distributed. So if I draw all of these, so you can see these things. Okay, but very important thing is you should note the observations. Yeah, I just showed you on the histogram, so you should again see what are the things that we can take out from these density plots, or you can take out from this box plots. What are the min value, what are the max value, what's the variance, how much is the mean in particular in those particular things. And okay, this is just one thing that you can do, but when you are working in the real world, okay, just remember this point. Very important thing is you won't be working with this such a simple data set. So here this is just to inculcate the thinking, how you should think. So the thinking process should be, okay, I have to check this, based on this single variable, what can I do, and then how can I mix and match 2-3 variables, can I do multivariate analysis. So all of these things should be done. I'm just showing you because I have seen, we have seen all these plots. We have seen this violin plot, box plot, and there are a lot more plots than this. So if you see this density plot, let's suppose, so density plot, in density plots you can see the density plot here, or if you see the petal length, it is bimodal. Okay, that you can also see from the histogram. If you see, let's suppose sepal width, it shows a sharp peak around 3.0. If we have this sepal width, if you see sepal width, density plot of sepal width, okay, I should have made it a little bit less. Sepal width, if you see a sharp peak over here, okay, so this is the sharp peak around 3.0. Yeah, I have just wrote these observations. So, and again, petal width shows the peak around 0.2 centimeter. If you see petal width, So you can see the peak is around 0.2 centimeters. So this is 0.0, this is 0.2, around this you can see a peak, and the peak you can see this is around 1.4, and you should write all these. Okay, the smoothness of this curve reveals the subtle patterns such as slight variations in these petal length and this petal, all these things. If you see these slight variations, okay, and you can see this Box-Cox plot, you can take outliers from there. Are there outliers? And based on these things you can say, okay, should I remove the outlier? We'll see an outlier treatment. And then we had these bar plots as well. These are Box-Cox plots and these are violin plots. And you can see this, okay, I count this pretty much 50-50 balanced data set, but sometimes you will see there is a heavily imbalanced also, so you should also plot these things. So now you can also see the distribution. So now you can see this is 33 point, because this is data set is handily crafted, so it looks somehow good, but in the real world it doesn't look such there are no such beautiful graphs. You will again see you have to clean and you have to do a lot of stuff in order to make it better looking. Okay, so this is the, and you can do a lot more than this, but just one point over here, this was not to show you the comprehensive list what can be done. This was just to inculcate that whenever you have data set, this is what you should do based on a single variable, what things can be done. Okay, can we do this, can we do this, and these are the things that that can be done. Okay, and I'll have more discussion on these plots again. I'll have more discussion on these histogram plots. Let me just show you some things and then we'll have a discussion, because the point is that I don't forget the goal. The goal is to somehow do something which should steer us towards coming up with a model, maybe a complex or simpler model, so that if somebody gives me those features, I should come up with a class label for that. I should come with a species. Okay, let me just make these distribution plots again. Okay, now I'll make them in a little bit different format. So if you see this, I'm making these 4 distribution plots. Okay, the question that I'm answering over here, let me show you the question I'm answering, and then I'll explain the code. Now based on this Univariate analysis, I have petal length, I have petal width, I have sepal length and sepal width. The natural question is, based on the importance of features, okay, how important are the features? Can I somehow do something? Okay, this feature is more important than this feature is more important. Can I do some ranking in these features? Okay, and how to know that? Okay, I'll show you just one method. Okay, this method may be rigged otherwise, and it let's suppose it may not work everywhere, but I'll just show the thinking process that goes into this. So the question is that which feature should be given more importance. So what I have done over here, if I just bring up the code window again, I'll explain you the code. So I am again making those histograms, but now this is a little bit different this time. So if you see, these things are setosa. Okay, this is the sepal length, and I'm just combining these plots together. Let me show you the plots and then we'll see the code. There are 4 plots in here because we have 4 features. Okay, there are 4 features and there are 4 plots. So sepal length has a plot, sepal width has a plot, and petal length has a plot, and petal width has a plot. So 4 features are there, and there are 4 plots correspond to that. And now what each of this plot contains, so this is that distribution. This is that, if you call it a PDF or a density plot for setosa. So if you see this one, so this is for setosa. So this is for versicolor and this is for virginica. Okay, and similarly you can see it over here. So based on this, so sepal length, because it has its own histogram, and you can have a density plot from that. So sepal length, if you just draw it for setosa, it will be this. If you again draw it for in the same graph, if I drew it for versicolor, it will be like this, and if I draw it for virginica, it will be like this. So this is what these graphs describe. So any questions on this? So what this graph describes? So I think it's pretty clear. So whatever we saw earlier, we were plotting this histograms, and after that we saw density plots. Okay, these are exact density plots, but now they are plotted on the same axis. Okay, this is axis AX. Yeah, so this axis is that you can call it a subplot or a figure over here. So in this figure you can see these are the things that we earlier saw, but here we combine them together. So again, don't forget the goal. The goal is to somehow understand the features, and based on these features come up with the label for that, come up with a species label. Okay, now the question that I asked myself is that, okay, I have 4 features. What features should be given more importance? Okay, and can I come up with a simpler model of some sort? So here if you see this, so now I'll explain the code before going ahead. So here if you see the code, again loading data set. So this is pretty standard that I have done earlier also. So now I have wrote a function that is plot feature distribution. I am giving the feature and the axis on which I have to plot it. So now I have used the Seaborn KDE plot. Okay, giving the data iris and the data frame. This is if the species is setosa. Okay, I'm taking the setosa and taking that feature and giving that color. So this is the function by which I plot this KD plot. Okay, similar for this. So I'm giving the species versicolor, virginica. So these are three functions which give me those KD plots, and then I'm saying whatever axis you give me, set the label of this, and set the X label, Y label, title, and the legends. Okay, and these are my features. Okay, or I'm creating these figures and axis. Okay, and I'm saying axis of flatten, and then I'm saying for feature and axis in this feature and this axis, and plot this one. And I think this is pretty clear. Okay, if you have watched enough of Python videos and enough of this matplotlib, you should be easily able to understand this code, and that's what the output of this code is, basically this. Okay, now how to do this? So if you see this, if you see the first plot, so if I say based on the sepal length, can I somehow come up with a species? Okay, so if it is, let's suppose from 4 to, let's suppose this is 4.5, say. So okay, I can say this is Setosa flower, but even still this is way mixed up. So all these density plots are mixed up. So I can conclude, but this is so messed up that I cannot conclude something which can not be concluded. And if you see, this is even more messed up. So basically what I want is, I want a graph like this. If somehow they are separated like this, somehow these density plots. So what I can do is, I can say if the length is this, so let's say I'll call it Setosa, I'll call this Virginica, I'll call this versicolor. If I have plots which are well separated, so what I can do is, I can make a simpler if else model. I can say if this it is this flower, if this it is this flower. So you can see it over here. Okay, let me go back. If you see this, so this is not good, the first one is not good, the second one is not good, the third and fourth one are a little bit better if you see these things. Okay, so this is Setosa. It is clearly, if I just write an if else program, I can say if petal length is less than, let's suppose 2.5. so if this is 2.5, this is confirmed Setosa. I'll have 100% accuracy based on just this petal length. You can clearly see that based on Setosa, I can clearly, if I have this 2.5, if there is a petal length which is less than 2.5, so I can clearly say this is Setosa. But here there's a little bit of jumbling, but not much, but still is cleaner. Okay, if you see this petal length. Okay, and then based on versicolor, I can make a model over there. If this is, let's suppose, less than 4 or something, so I can just make an if else model based on this petal length. Okay, based on this petal width also, this is also good, because if petal length is, say, less than 0.7, this is confirmed Setosa. Setosa flowers can be easily distinguished from the non-Setosa flower based on this petal length and petal width. So can you now tell me one thing? So I have given you the principle. Can you see it over here? Sepal length, I couldn't conclude anything because the problem was they were so much overlapped, and this sepal width was way too overlapped. Now if you see this petal length and petal width, they are much cleaner than this. Okay, so what I think is, this petal length is a bit more clean, because you can see over here there is a lot of gap in here. I can conclude things from Setosa. There is less overlap over here also. Okay, I think similar overlap overall over here. So can I say this petal length is the most important feature? If I just want to use one feature, okay, this is having some distinguishing properties. Can I assume this? Okay, why? Because you can clearly see that if I just write a simple if else program, if I just write a very simple if else program, I can say if petal length is less than 2, confirm Setosa. Okay, I'll get 100% accuracy for this, 100%. Now I can just boil down a problem to this. I can make a machine learning model only for this, let's say. Okay, because I somehow truncated 33.33% of my data. I don't need any machine learning model for this now. Okay, and I made my model simpler. This applies to all the queries also. If you are doing something online, if a single if statement simplifies the model, and you can see that now it only has to learn this much. Okay, if somehow these two are also separated, okay, if I can do this, if I can just make a line over here, I can say, let's say else if petal length is less than 4.5, so this is versicolor. So from this you can see, again there will be some inaccuracies, okay, because some flowers will fall over here, but still I had made a if else model. So do you agree on this? So from this what I can assume is petal length is important. It's much better than petal width. This is much better than sepal length. This is much better than sepal width. Can I write this order of this importance? How many of you agree on this order, and why? If not, why? Okay, so this was introduced in order to, because we are seeing towards a goal. The goal, you should not forget, the goal is based on the features come with the species. That's the goal. Okay, the question that I asked is, okay, if I now have to choose between these things, because let's suppose I have a lot of features. Based on this, if I have to just choose one of the feature or two of the features, which are the features I should choose? So based on discussion we had in last 10 minutes, so I said petal length is a better candidate and then this petal width. This is a better candidate than this, and this is the least candidate. So if you just want to drop one feature, so you should probably drop this petal width, because this is too much intertwined. If you see this, if you see the distribution of this, if you see these density plots. Okay, just let me zoom it and I'll show you if I just have to make an if else program, how I'll make it. Oops, I think we need to work with this only. So let's say I'll be over here. So now what point should I choose a threshold? So I have to now choose threshold, because over here this is pretty clear. So because if the point is less than 2.5, confirm setters are 100% accuracy, and I have truncated a lot of data from this, and it made my life simpler, because Setosa flowers I can distinguish them very easily. I can differentiate Setosa and non-Setosa very easily. And now coming to this, so why should be the threshold? So if I, let's suppose, put the threshold over here. Okay, if I put the threshold over, let's suppose this threshold is somewhere around 4.4, let's say. So this threshold, so this is 4.4. So the threshold is this. So now what we will do is, so if you are saying is the first condition is if petal length is less than 2.5 Setosa. Okay, then we are making else if petal length is less than 4. Let's say 4.4, then it is versicolor. Now the question is that how much inaccuracies will be there. So okay, you will see that a lot of things, because if you see these points, this much points, these many points are from the Virginica class, but they will be categorized as Setosa. This is the first problematic thing. And then the second thing is we'll miss this much portion, and we'll miss this much portion will be missed, and we'll miss these things. Okay, they will be considered as, let's suppose, Virginica, and from this Versica there will be a lot of inaccuracies. Now I have to somehow set this threshold. So why should I set the threshold? So the threshold should be set over here. Why is it so? Let me explain you why is it so. If I set the threshold over here, okay, now if I say that this threshold is 4.9, if this threshold is 4.9, let's say, okay, if the flower is on this side, okay, on this side, so it has higher probability of being vertical and less probability of being versicolor. Why? That you can see these from the density plot. So if I take a point from here, if I take a point over here, say over here, I am taking a point over here. So now if you see the probability over here, because these density plots some also show the probability. So a lot of flowers of Virginica color follow this. So there is a higher probability that this flower will fall into the Virginica category, because now if you see there is a little probability. If you see this much probability, I should differentiate it clearly. So this is the point. Let's suppose if it's on this side, oops, if it's on this side over here, what I'm saying is this point, if any flower has a petal length greater than 4.9, so there is a high probability that the flower will follow into this versicolor category. So what I can say is, based on the probability, I should assume that this threshold, based on this threshold, so because it is somehow dividing into two spaces again, so there is this side and there is this side. Okay, so if a point is on the right side of this threshold, so there is a high probability that it will be from the versicolor, that you can clearly see from the density plot. And if it's on the left side, you can again see that there is a high probability it will come from this versicolor. Here it's Virginica. On the right side there is a high probability it will belong to Virginica. On the left side there is a high probability it will belong to versicolor. So that's why I have taken this threshold where they intersect together. I should not take the threshold here and there, basically out of the intersection. Why? Because you can clearly see that if you take this point, the high probability of this point being Virginica is more, okay, than versicolor, because versicolor is this much and Virginica probability is this much, basically higher probability. Again the same thing for this side, same thing for the left side. So if I just write in blue, if we have a point over here, okay, there is a high probability, this much probability that this point will belong to versicolor, and there is only this much probability that this point will belong to Virginica. So it's a good decision from probabilistic perspective that the threshold should be, we should choose this threshold, and we should choose the threshold this because somehow probability supports it. Because if a point, data point belongs to the right side of this, it has high probability of being versicolor. That's why we'll write in if else program. We'll say if petal length is less than 2.5, this is confirmed Setosa. Else if the petal length is less than 4.9, so this is versicolor. Why? Because anything that's on the left side has the high probability of being versicolor. And then we'll say at the end, else if the flower is, let's suppose, greater than this, so it will be Virginica. Why? Because on the right hand side of the threshold there is a high probability that the point will belong to the Virginica. Still will make some inaccuracies, there will be some wrong classified points, but we can somehow manage that. But if you see probabilistically, so you'll make now less errors, okay, because probability supports you now, because if you are categorizing it this way, so probability will support. That's how you should choose the threshold. Again, not to show you that this will apply to everyone, I'm just teaching you the thinking process that goes into this. Okay, I'm telling, okay, if I just have to make an if else program, let's say here I got 100% accuracy. Let's suppose in this Virginica I got somewhere around 85% accuracy, somewhat like this, and here I again got some, let's suppose 90%, something like this. I'm just making rough numbers up. So now you can see, if you combine all of these together, if you somehow got an accuracy of, let's say by combining all of this together, so if you somehow got accuracy of 90%, say some 90%, by just saying writing if else program, just writing 3 if else conditions, so do you require machine learning? Okay, if the thing was so simple, okay, people will come up without doing data analysis, they'll make a complex model which will have, let's suppose, some if not billions, if not millions, maybe thousands of parameters, and they'll do the same job, and maybe they'll come up with the accuracy of 93%. Let's say they'll come with the accuracy of 90, and you just wrote 3 statements, if, else, if, and this, and you came up with a program, and your model is giving 90% accuracy. So what should you go with? Now, because you have such a simpler model, the first thing, you have such a simpler, you have nothing, no parameters to learn, no training, nothing. Okay, and inference is almost instant, or you just give, it just checks the if else condition. Okay, it's just a program. Okay, if you can do this analysis, so it's way better to use this model than to go with the deep learning. Okay, that's why this analysis is very important. If you can do this, and you can see this sepal width is not important, I just remove it because I have a lot of features, just remove it, because you can see it does not convey much information, it's not that distribution feature based on whatever you observed. Okay, that's why this is important. How many of you understood this portion? Because this is very important, because I said this is to inculcate the thinking. Okay, what should be taught? Okay, because if I have to just make it. Any questions on this? So takeaway from this is, if you can somehow observe some things, and if you can make a model a little bit simpler, so it is better to go with this. Why? Because sometimes you can get an accuracy of maybe 93% if you use a model which is very complex, and if you use a very simpler model, if you get, let's suppose, accuracy of 90%, I'll always go with this. If this is not a critical application, if the application is not, let's suppose, if the life is not dependent on that application, so you should go with, let's suppose, this. Why? Because inference time is almost near to 0. Here you'll have a lot of inference time. Here you have to train, and even what analysis we did, if you somehow even could truncate the data only, because here set was a flower, if you just wrote one if condition, okay, if this is that, don't go to the machine learning model, just truncate it. Okay, just give the results by using the if else. Maybe if you have doubts on the other two parts of the flower, you have setosa, you have this versicle and the Virginica, because there was some overlap that we saw in the figure, that we saw in these density plots. Maybe for those you can train the machine learning model. Okay, because for setosa you will be clear, because you are now from this multi-class classification, what you did is you made the binary class classification problem. We had 3 classes, you just analyze few things, and you said, okay, based on a petal length, I can be sure that this is a setosa flower, because that's what I saw from the data, that's what I understood from the data. Now I convert into binary classification problem. I now just have to classify into 2 classes. Okay, if somehow it is not in that threshold, if it is in that threshold, I'll say, okay, this is setosa. If now it does not belong to that threshold, after that I'll use machine learning. The pipeline will look like this. If a person is making inference, okay, it gave a data point, so what you will do is, so the first thing is you will cross it through a if condition. So if setosa, if the petal length, because it will have petal length, if petal length is less than 2.5, okay, if it was, you will directly answer it from here, you will say setosa. Okay, if not, then go to the ML model, if it is so complex, if you are thinking that, okay, if else conditions cannot do justice, and this will help you in many things, because when you are seeing the fraudulent, if you are working in banking sector, if you are working in healthcare sector, if you see a variable, if you see a feature which you can see by if conditions, because that's a very indicative feature. If that feature is very indicative, and if you just see it and you can say, okay, this can belong to this, I don't need a machine learning model for this. So what you can do is, you can, based on that, you can save a lot of inference time also. You can also save a lot of training time. Okay, your model training basically starts from when you do this EDA. Okay, that was the point, to show you this importance. Okay, again, to reiterate, we should have the goal in mind. The goal was, based on the features, you should classify it into species, you should say which species it is. And now I asked simpler question. I said, okay, the question is, what is the importance of feature? If I want to drop a feature, okay, which should I drop? If I want to just pick the topmost feature, which should I do? I just had some density plot, I did some analysis, and this, I think I'll end today's session over here, and I'll end univariate analysis over here. So from next session we'll take bivariate and multivariate analysis, and maybe we'll intertwine them together. If you have any questions, I'll be taking them now.